here's a picture of a really pretty waterfall. Pretend that over on the far end here, there's a pump that brings the water back up, and then it loops around, and then it goes over the waterfall. And this is just a continuous flow. So pretend the river doesn't start elsewhere and end up in the ocean ultimately. Instead, it's just a contained closed loop with a pump and with a waterfall. Now, the waterfall is, in this analogy, kind of like a resistor. The analogy breaks down because resistor slows the flow of current, waterfalls pick it up, so that's not perfect there. But it's a really good analogy in other ways. So as water goes over the waterfall, it loses some potential energy, some gravitational potential energy. You started at one height, you ended at another. That change in energy had better be the same change in energy that the pump provides, because I need to be back up to the same starting point before I can go over the waterfall again. I'm not going to go up any higher or go up lower. I'm going to go up to the same height. So in one direction, it's losing energy, then the pump lets it gain energy. The pump is basically an analogy for the battery, and the waterfall is an analogy of the resistor. Here's what a similar circuit would look like. The symbol for a battery is typically a small line parallel to a big line. The big line is typically the positive terminal. The small line is typically the negative. And if you got multiple cells lined up, then you may draw multiple. I kind of alternate between just one combination and several when I do it. But that's the battery symbol. The resistor symbol is this weird squiggly line. That's what adds the resistance to it. So, by the way, conventional current flows from the positive terminal of the battery to the negative terminal of the battery. Now, what kind of charges would do that? Well, positives are repelled by positives and attracted to negatives. So much like the electric field, conventional current is what a little positive charge carrier would do throughout this circuit. We have since realized it's electrons that are moving around, but we were too lazy to change our conventional current direction. So in this class, we're going to go with conventional currents, pretending like the charges that move around are positive. They're really negative. They're really going in the opposite direction. But it doesn't matter because all our numbers work out regardless. When you leave the battery, you're at some high voltage. When you go over the resistor, you drop off your voltage just like that waterfall, and you're back down to 0 volts before going back into the negative terminal of the battery, where it acts like a pump and brings you back up to a high voltage, where you drop it off at the resistor again, and this continues over and over and over again. Now, waterfalls can get a bit more complicated than just one single drop and we're done. Some waterfalls have a series of steps. Now in this case, I'll drop some potential energy off at waterfall 1, I'll drop some potential energy off at waterfall 2. They're not necessarily going to be the same. In this picture, it looks like U2 is a little bit bigger than U1, but when the pump brings it back up, then the grand total, U1 plus U2, needs to add up to whatever energy the pump is adding to it. So I could find the energy that the pump is supplying to this water molecule just by simply adding the total of the drops, the total from the waterfalls. It's the same thing over here on circuits when you get a couple of resistors in a row. So as current leaves the battery, goes over resistor 1, it drops some of the voltage off, but not all the voltage from the battery. When it goes over resistor 2, it drops some of the voltage off, but not all the voltage from the battery. But when you add up V1 plus V2, it will equal the total voltage from the battery, so I'll be at 0 volts before going back into the negative terminal of the battery. Just like you're at 0 height before you go back into the pump, brings you back up to the top, you go over your little step waterfalls again. This is what's called a series circuit. By the way, if you haven't noticed from these waterfalls, all of the water that comes out of the pump goes over waterfall 1, and all of the water that comes out of the pump goes over waterfall 2. There's nowhere else for the water to go but through both resistors. It's the same thing with our circuit. All of the current that comes out of the battery also goes through resistor 1 and it goes through resistor 2. Because there's literally nowhere else for these electrons to go, there's no place where the circuit splits off and gives it a choice of paths. All the electrons that come out of the battery go through R1 and R2 in a series circuit. Now, the reason I bring that up is because sometimes current does split in nature with waterfalls as well. When this happens, the total energy that's dropped is the same whether I went over waterfall 1, waterfall 2, or waterfall 3. Oh, whoops, I wrote 2 twice there, didn't I? There we go, that's better. So, whatever path I go over, I'm starting at one height, I'm ending at essentially 0 height. And then I'm having the pump bring it back up, and that total change in energy provided by the pump is equal to the drop at 1, or it's equal to the drop at 2, or it's equal to the drop at 3. It's the same thing in what's called a parallel circuit, when I have multiple different paths I can choose, but each path only sends me through one resistor. In that case, I gain voltage from the battery, the pump lifts me up, and then, if I'm an electron, I start leaving the terminal of the battery, I come to this first junction point, and I can either go to the right, or I can go down. But I can't do both. As a single electron, some of my other electron friends will make the other decision. So the current splits, just like with the waterfall. Some of the water goes over waterfall 1, some of the water goes over waterfall 2, but the same single molecule is not going over both. So the current splits, but no matter which path you go down, you're still dropping the same total voltage, because when I get to the bottom, I better be at 0 volts before I go back into the battery. So in this case, my total voltage equals voltage 1 equals the voltage over R2. In the series circuit, our total voltage is added because it was a series of steps. Now, I'm still traveling over just one big waterfall and I'm done with it in this sort of a circuit. So the total voltage is the same in parallel. What's different is with the series circuit, all the current that left the battery went through both resistors. That's not the case here. Some of the current chooses path 1, some of the current chooses path 2. So here I'll have I total leaving the positive terminal of the battery until I get to the junction point where I'll call I1 the current that goes through R1, I'll call I2 the current that goes through R2. By the way, there's a junction point down here. So I1 arrives at this junction point, I2 arrives at this junction point, and then they both travel together back to the battery. So I'm back to I total when I get back to the battery. So when it comes to current with parallel, it simply adds to the total when you bring all the paths back together. So that's the main difference between series and parallel. Now, of course, you'll also end up with some waterfalls where one path you take, you have a series of steps within that path. Another path, you're dropping all off at once. Sometimes it can become a huge mess where you have some parts of it that are in series together, and you have some parts of it that are in parallel. So here's my series, here's some parallel branches. So we're going to work on how to break these circuits down because it gets a little more complicated, but we'll do that in class later.